Okay, like I said, I wanted to go over the last couple worksheets very, very quickly. I also wanted to talk about what it means in terms of what we've done so far, in terms of kind of Unit 1, summarizing stuff that you need to know. Um, so right away, we've got some questions, we've got a model, and it's asking us about comparing mass and volume and density, so how we think about that. And I think we even started talking about this right at the beginning when we started the worksheet, but I am going to be going quickly. I do recommend you make little notes on your worksheets. This video obviously will be on Google Classroom for you to check out later. All right, so we're comparing these two objects here. We have object A and object B. Which one do we say has more mass? Okay, B has more mass. Why? Okay, so the larger side goes towards B. It has more particles, which we would think of as dots. Okay, remember we don't want to be drawing circles. Don't be doing that. Just be making dots for particles. So if we go to summary, that tells us two things right now. We've got mass. We could say number of particles or amount of matter, which kind of started talking about amount of stuff. How much stuff is in something that's mass. Another thing, something we do with models. Particles are dots, not circles. All right, check. Good. All right, what about volume? Which one has more volume? Dre. B. Does everybody agree? If I see a hand, that means somebody disagrees. All right. So I'll make the larger side of the angle towards B, saying that B is larger. What do you mean by that? Why is B more volume? B is bigger. Okay? So here's another concept. Volume. All right? How big something is. Okay, but realistically what we say is the amount of space something takes up. Cool? All right. Which one has more density? Here, A? They're equal. How many people think A? Raise your hand. Who said A? Why do you think A? A, so do you think they're equal? Raise your hand if you do not think that they have equal densities. Okay, so equal. Why? Spacing of dots the same. Cool, so there's our density concept. All right? How spaced out particles are. We know that it's the mass per volume, right? Mass in grams. Okay, so we know that this is in grams up here. Volume could be in a couple different things. Could be in milliliters, could be in cubic centimeters. It depends on how we're finding volume. Okay, so volume, milliliters. I don't want to do that. Or cubic centimeters. Okay. Or how compact the particles are. So just by saying what we have here does not necessarily, just by reading those, does not necessarily tell me if you know what density is, because I could say, all right, what does that mean then? If particles are really spaced out, it has a low density or it has a high density? If the particles, well, I could say that, but let me actually ask the question. If the particles are really spread out, would that be low density or high density? Okay, so let's make a note of that on here. Spread out equals low density. All right, cool, we got that. Good? Any questions? All right, number 2, similar idea. I shouldn't really have to go back to what we had before. Go away, go away. All right, so what about on this one? We've got 3 objects. We've got A, B, and C. What about if we just compare the mass of A and B? Dre. A has less particles than B. Does everybody agree with that? Any disagreements? Raise your hand. Any disagreements? Raise your hand. A has less mass than B. Okay, so I'm going to put the lower end of the angle towards A, meaning it has the smaller end, meaning less mass than A. What about if I compare A to C? Same thing? And how do we know that? Cool. All right, what about volume? Compare A and B. What is volume again, real quick? Amount of space, how big it is, right? So volume between A and B, which one is smaller? A. What about between A and C? Equal. Same size, right? So understand, this is where people get tripped up and confused. Mass is the particles. Volume has nothing to do with the number of particles. It's just how big is the overall object. It has nothing to do with particles. Does everybody understand that? So why would we say this? So what about A? We could say A is smaller than B, but same size as C. All right. What about density between A and B? Equal? Anybody disagree with equal? What about between A and C? A is more dense. A is less dense. Why do you think it's more dense? Why do you think it's less dense? Less space in which one? A has less space between particles. C. It's more packed, right. C has less space between particles, which means it's more dense. Okay, are these any new concepts than what we had before? What's the point of doing this one? We just did all this on number 1. What's the point? Yeah, last time we were just comparing one to another. Now we've got to consider some different things with 3 of them. So 1 compared to 2 other ones. All right. We could see where they'd be the same size. Between A and C, they're the same size, but since C has more particles, same volume but more particles, more dense. We can see between A and B that they have the same density, but because B is larger, has more volume, and because it has more particles, it has more mass, so it's like we increase the mass and increase the volume, and by increasing both of them, we keep the density constant. We're not changing it. It's like B is just a larger sample of A, really. Okay? So really no new concepts there, except, I guess, the relationship, what I kind of mentioned, if you watched my video yesterday, which I'm sure you guys all rushed home to watch that on Google Classroom. But as we saw there between A and B, some relationships, if I made the volume bigger, oh, let me think here. I don't want to mess you up. Okay, between A and C, they're the same size, so same volume, but C, we increase the number of particles. So if we increase the number of particles, we're increasing the mass, right? And by doing that, if we increase the number of particles, we also increase the density. Yes? So what we see with these arrows going the same way, what we call this is a direct relationship. Okay? So what do you think would happen if I kept the volumes the same, but I decreased the number of particles? What would happen to the density, do you think? It would decrease, right? So decrease mass, decrease density. Okay, now going the other way, let's say we didn't change the mass. Okay, maybe I should make a note here. Volume constant, what does constant mean? Continuous, consistent, not changing, right? Okay, so let's say we keep the mass the same, the number of particles the same, and we've got this object, it's about this big, and it's got 5 particles in it. And then I increase the size, I stretch it out to this big. Okay, so I increase the volume, right? But I kept the mass the same. What would happen to the density? So if I increase the volume, the density would do what? Get smaller, that's right. So volume, if I increase the volume, the density actually goes down if the mass is constant. So when they go opposite directions, what we call this is an inverse relationship. And what that helps us understand is that that's why the equation looks like this. Density and mass are both on top. They're a direct relationship, straight to each other. But density and volume, one's on top and one's on the bottom, that makes them inverse. Just something interesting. So guess what? If I kept the mass the same but I decreased the volume, what would happen to the density? It'd go up. That's right. All right, so much for going fast, Mr. Dodds. All right, number 3, is object E or object F more dense? Assume the particles are uniformly distributed throughout each object and particles with a larger size have a larger mass. Explain your reasoning. Ooh. E would be more dense. Does everybody agree with that? Why? Can I say less space in F? Okay, so 13 dots is what I count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So they each have 13 particles. These ones have more mass. Okay, so if we've got more mass in the same volume, we're going to have a higher density, right? That's what we were just talking about in the last part. All right, cool. Getting closer to the end here, right? Oh, no, we're not. All right. Number 4, in figure 4 below, a graph shows the relationship between mass and volume for 2 substances, A and B. Use the graph to answer the questions about these 2 substances. All right, so here I want you to notice we have mass on the Y, we have volume in milliliters on the X. Okay? So when we draw these best fit lines here, what do those best fit lines tell us? You have to know this. Yeah, really, you got to talk about the slope of best fit line means what? What does that show us? It does show us the points. I mean, we make a best fit line through the points, right? Because we plot those first. Ashley? The relationship between the 2 variables that we're graphing. And really what it shows is it shows ratio of y variable to x variable. Because it's the rise over run, right? Rise being the change in y, run being the change in x, that's the x variable. So on this graph that we're looking at, what it's showing us is a relationship between mass and volume, or mass over volume. And what is mass over volume? Density. So if I calculate the slope of the line, you should know that the slope of these best fit lines is the density. Okay? Cool? All right, so we've got substance A. Can you just tell by looking at them which one has a higher slope? A has a higher slope, so A would have a higher density, right? Okay? So you, blah, 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 blah. What would happen to the balance if you put equal masses of A and B in the two pans? If you put equal masses in a balance, two pan balance, is it going to tip one way or the other? It's just going to stay the same, right? What if I put equal volumes of A and B? So say I just picked out a random, like let's say we put 20 milliliters of each. Okay? It is going to be different. That would mean B would have a mass of 10, and A would have a mass of like 35 or so. So what would happen? Two pan balance would dip down towards A's side, right? I'm not going to write all that. It's on the video. Good? Find the slope of the line for both A and B using correct units. State the physical meaning of the slope for each substance. Okay? Slope of A and B. So slope. Start and go left to right. And these are both uphill graphs. They go uphill as you go left to right. So that means they have positive slopes. Now I'm going to talk about negative slopes right now. So every slope we find is positive. But here's what you got to make sure that you do is go left to right. Okay, going left to right, starting with A, I want to look for points that are easy to read. Like ones that go right through the middle. See how this one goes right through the middle between 20 and 30? What does that mean? 25. And it's right on the 40 grams. So that spot right there is 25, 40. That's how you do the coordinates of the dot. All right, let's find another one that's easy to read if there is one. Oh, this is kind of easy to read right here. It's a volume of 50 and a mass of 80. So that would go 50, 80. Always put the X number first and the Y second. Everybody got that? So if I want to do the slope, the first dot I picked out, what that is x1 and y1. And the next one is x2 and y2. If I do the slope, I want to do y2 minus y1 over x2 minus x1. So y2 minus y1 would be 80 minus 40, which would be 40. Right? Y2 minus y1. Did somebody disagree? Okay. Everybody staying with me? I know this type of lesson, it's a review kind of and practice. I know it's not super exciting, it's boring, but try to stay engaged. Now I'm going to do the same with x2 and x1. So if I take 50 minus 25, what do I get? 25. Does anybody have a calculator handy? What is 40 divided by 25? Yep. Okay, so the slope of that line is 1.6. What does that tell us? It tells us 1.6 mass over volume, or grams over milliliters. Hey, that's density, 1.6 grams per milliliter. All right, let's do B. Find a couple spots that are easy to read on B. Okay, this spot right here kind of looks like it goes in the middle there between 0 and 10. So I'd call that spot maybe 10, 5. That cool? All right, is there another spot that's easy to read there? This is kind of easy. That hits this line right in the middle between 20 and 30, and right at 50. So 50 and 25. Does that make sense? All right, so if I take y2, my second dot, and subtract y1, I'm going to get 25 minus 20, which would be 20 over. And then the x2 minus x1 would be 50 minus 10. And I know that one. 20 divided by 40 would be 0.5, right? And what does that mean again? Y variable, use units when you can, over x variable. Density again. Okay? Okay. Do you guys want me to go over these, or want me to go over all of them? If you put 10 milliliters of A in one balance pan, what mass of B would you need in the other pan? If I put 10 milliliters of A, what would be the mass of 10 milliliters of A? Well, here's 10 milliliters. Go up to the A graph. It's right here. What is that? 15 would be right in the middle. Looks like a little more, like maybe 17 grams. So what mass of B would I need to have on the other side to make it balance? 17 grams. It's pretty simple. Okay. Letter D, if you put 35 milliliters of B in one balance pan, what volume of A would you need in the other pan to make it balance? So if I had 35 milliliters of B, 35 is right in the middle here, go up to the B line, right about there. What mass would that be? That's a little closer to 20. I might say 19 grams on that one. This is letter D. All right, so B would have a mass, 35 milliliters would have a mass of about 19 grams. What volume of A would I need in the other one to make the pan balance? So basically, what volume, if I have 19 grams of A, what volume would that be? So if I go up to about 19 there, kind of where I was at with the 35, if I just go straight across and hit A, what volume is that? Looks like it'd be 10 milliliters. Is that what you guys had? Something close to that, maybe? No? Water has a density of 1 gram per milliliter. Sketch the line representing water on the graph. Let's do blue for water. How am I going to do a slope of 1? If I had 10 milliliters of water, how many grams would it be? 10 grams, right? So I can make some dots to start, or I could just go straight through them. Make a line that goes to 10. What if I had 20 milliliters of water? How many grams would I have? 20 grams. What if I had 30? Something like that, right? And then the next questions ask you about sinking or floating. So remember when we did the lab and I had you add the vegetable oil to water, and the vegetable oil was floating on top, right? Wasn't it? Okay, so if it floats on top, does density have anything to do with floating, do you think? There's a reason why we're seeing these questions on here. Yeah, if something is less dense, it floats. So the vegetable oil, if it floats on top of water, should have been less dense. All right, so if we have water and we've got substance A and we've got substance B, and I put substance A into water, do you think it's going to sink or float? Raise your hand if you think it would sink. So I only have 2 people that think it would sink. The rest of you think it would float. Janiyah, why do you think it would float? Sure. Okay, so I've got substance A, I've got substance B, I've got some water. I've dropped substance A into water. Would it float or would it sink? It would sink. Raise your hand if you think it would sink. Why would it sink? Who can tell me? Bigger mass, is that right? What determines if something floats or not? Density, so it must have a higher density. If I find the slope of substance A line, is that a higher slope than water? Which means higher density, right? So if I put B in, what would B do? Float. Why? It's less dense. I can tell because the slope of its line is less. Make sense? Can you tell that the slope of the lines is going to be probably pretty important on a test? All right. Defend your answer. We just did. Okay, some people really struggle with this. Sketch a graph of mass versus volume for titanium, copper, and mercury. All right, so how am I going to do titanium? Well, we have the density here of a bunch of different substances. This might be important to note on our summary. This doesn't say a volume. It doesn't say a certain mass. It says a certain density for aluminum. Well, what if I have different amounts of aluminum? What's the density going to be? 2.7 grams per milliliter. What if I had 1,000 pounds of mercury? What would its density be? No, just 13.55 grams per milliliter. What if I only had 5 pounds of mercury? What would its density be? 13.55 grams per milliliter. These densities are constant for different substances. Different substances have different densities. And since a substance has a specific density, density can actually be used to identify a substance. Did you see a question on there, something about a ring, a gold ring, something like that? What was the point? Well, we wanted to find out if the density was really the density at which gold should be, right? I was curious about those BBs that we used in the lab. Are they really truly pure copper? That sounds like a CER to me. All right, so this is all you got to do for this. This is how easy it is. What color you want titanium to be? Red? Great, because I've already got it. The density is 4.54 grams per milliliter. So if I had 1 milliliter, how many grams would I have? 4.54 grams per milliliter. So if I have 1 milliliter, how many grams? Glenn? Yes. How many grams would I have? 4.54. So this is set up here. It looks like each mark on the volume scale is 1. So for titanium, for a volume of 1 milliliter, I'm just going to mark 4.54. Now the mass, 10, 20, 30, 40, 50. All right, so 4.54 would probably be a little less than half, which is not really easy to do on here, but as long as we're close. All right, well, what if I had 2 milliliters? Just multiply by 2, right? 4.54 is going to be about 9. So I'll go to the second mark for volume and do, I keep missing the line here, but a little less than 10. All right, I could do this for all of them, or what I could do is get a couple marks and then maybe multiply by 10, which would be easy to do. All right, because we know that the density line is going to be a straight line, don't we? I mean, all we're doing is we keep increase. This is a slope. It's telling me every one I go, it's going to increase by 4.54 for titanium. So if I went to the 10th mark, that'd be 4.54 times 10, which is easy. Just move that decimal one spot, 45.4. So let's go to 10, and let's kind of just go, where's 45? About like that, okay? And then if I could draw a straight line through these, I should make the slope of the density of titanium. Now let's talk about what we call the y-intercept. So the y-intercept is where your line that you graph hits the y-axis. Because we could have graphs that like come through here, up here. Okay, that would be hitting the y-intercept somewhere just above 70, or maybe they hit here, like at about 35. All right. Do you think the y-intercept in these density examples should be 0? Gabriel says yes. Why do you say yes, Gabriel? He says that the y-intercept should be 0 because if you have 0 volume, 0 milliliters, you should have 0 mass. Does that make sense? Okay, so that just gave us another point, 0, 0. So that means I could start here and go through those 3 dots. Forgive me if it's not straight or through the 3 dots, but something like that. Okay, boom, density of titanium. All right, let's do copper. Let's make it green. Copper is 8.96. So at the first mark, I'm going to mark it at about 9. Second mark, I'm going to mark it at about 18. If I multiplied by 3, it'd be somewhere around 27. I'm just kind of rounded it off to 9. This doesn't have to be exact. 3 would be 27, so maybe about there. If I multiplied it by 10, it would be 89.6. So just below 90. So does it look like I can make a line through those dots that hits the origin? Maybe. Oh, not starting like that. Close enough. Copper. Pretend it's a straight line. Last one, mercury. Blue. I can just look at it. Do you think the line is going to be steeper or flatter than the green and the red? It's going to be steeper. Okay? So it's going to start at 0, and by the time it hits 1, it's going to go through like 13.55. So it's going to go maybe something like this. All right? That's how you do those. If you're really good at it, you know that the density slope should be 0, 0 through the origin. Do the first dot, and you can make a straight line through those 2 dots, and you'd be done. Let's try and go fast. I know this is not very fast. Try it. I know you guys wanted some help with yesterday's, right? Okay, so let's take a look at today's, or yesterday's, sorry. All right. So what we have is we have two substances. We have metal A, which is the top line, and we have metal B, which is the lower line. So which one has a higher density? A. How do you know? Which slope is steeper, the red one or the blue one? Okay. So that tells me red is steeper, it means a higher slope. Okay. Which means in this case, when we're doing mass versus volume, higher density. Okay. So A is a higher density. Determine the density of each metal. How would we do that? Karen, any ideas? What would we do? How do we find slope? Y2 minus Y1, X2 minus X1, right? So we got to pick two dots. Find two dots that are easy to read. So we have some marks going along here. It looks like we go by tens for mass. Looks like volume goes by ones. All right. So same thing that we did last time. We try to pick a couple marks that make sense. Maybe they go through the middle. These lines aren't very easy to read. This might go through the middle here. Ish. Okay, so maybe I could make a mark at 2.5 and 30. Now I did see some people yesterday were doing two different marks on two different lines, or two marks, one on each line. You can't do that. To find the slope of one line, both points have to be on the same line, right? Okay, is there another easy mark to see? Maybe right here, which is 4.5 and 50. So if I wanted to find the slope of A, I'd just do 50 minus 30, which would be 20, over 4.5 minus 2.5, which would be 2. So maybe you guys got a slope something like 10. Somewhere close to that, maybe? So let me ask you guys, you sound like you really wanted me to go over this. So what part of this do we not understand? Let me have you guys ask me questions. Have me go over a problem so I can be done. I know you guys were losing it like 15 minutes ago. Okay, Janelle? Picking two spots. Okay. Any other questions about the worksheet from yesterday? Trying to find the density. Number 5. Oops. What is it? Excuse me. What is the density of water in grams per milliliter? What does that mean? Does anybody know the density of water? It is 1. Convenient, huh? It's 1 gram per milliliter. What does that mean? For every 1 gram, there's 1 milliliter? Could you say it the other way around? For every 1 milliliter, there's 1 gram. Yep, same thing. Janelle? Number 10? I could go over other ones if you want me to. We've got about 6 minutes left. Number 10. And Mac, you got one you want me to go over? All of them? Okay. All right, so a standard backpack is approximately 30 by 30 by 40. What are they going to have me find? I already know. What are they going to have me find? Volume. 30 by 30 by 40. What is that? What is it? 36,000? Is that right? Ooh. Open up a billion calculators. $30 times 30 times 40, 36,000. Okay, so standard backpack is 36,000 cubic centimeters. All right, suppose you find a hoard of, is that what it says, a hoard? Of pure gold while treasure hunting in the wilderness. How much mass would your backpack hold if you filled it with the gold? So what they want to know is they want to know what is the mass of this volume of gold. Any idea how we could figure that out? And I know as I looked around, this was a problem that most people did not have an answer to. Well, so the density equation, density equals mass over volume. There's three variables. There's density, there's mass, and there's volume. You have to have two to find the third. Is there any way we can find the density of gold? Janelle? It was that table you had on here? Oh, was it right in number 8? Gold is on the table. On that table for number 5, it says gold's density is 19.30 grams per milliliter. So AU density, 19.30 grams per milliliter. Could I also just say grams per cubic centimeter? Same thing, right? All right, so I have some variables I could plug in here. I have 19.30 for density. I don't know the mass. We're trying to figure that out. And I know the volume is 36,000 cubic centimeters. So how would we find the mass? What's that? Volume times density. Thank you. I couldn't quite understand. All right. So that means we can just take, I could multiply both sides by 36,000. Oh, that's not what I was trying to do. Can't move it. All right, but yeah, that's what we would do is we'd multiply both sides by 36,000, which would cancel this out, times 19.30. Oops, it was already on there. 19.3, same thing. And so that tells me I would get 694,800 grams would be the mass of that. Okay? So an average student has a mass of 70 kilograms. Do you know what the relationship is between a kilogram and a gram? It's 1,000. Yeah, there's 1,000 grams in a kilogram. So they're saying the average mass of a student is 70,000 grams. How do these values compare? Would they be able to carry it very easy? They'd be carrying several times their own body weight, wouldn't they? All right. I will go over one for this worksheet, more tomorrow.